Now that we have been introduced to the idea of limits, let's take a look at a few example problems together. In our first example here, given the graph of f of x equals x plus 4, evaluate the following limit. So we're looking down here. We want to find the limit of x plus 4 as x approaches negative 3. So we can rewrite this to match what we saw earlier. And we have the idea that it's the limit of f of x as x approaches negative 3. So we must consider the limiting value of the function, both from the right side of x minus 3 and the left side of x minus 3. And so what happens when x is equal to minus 3? That is going to be right here in our graph. So we go up, find our point, and over to find our output value or our y value. Now, we notice that there's no holes shown in the line. This isn't a rational function. There's no gaps. There's no x values that aren't allowed. I can have any value of x that I want. And so all I'm really doing is just evaluating here. So all I have to do is f of x equals x plus 4 is evaluate my function for x equal to negative 3. And I get negative 3 plus 4 is 1. And so the limit is equal to 1, or I can just write here the limit is equal to 1. If the limit does not exist, then we would just put dne, or if it approaches negative or positive infinity. But in this case, because our line is continuous, is defined everywhere, there's no gaps we need to worry about, we can just evaluate. Or we could consider, like we did with our table of values, maybe there was a hole here, we couldn't actually get this value. But as I have values of 3 that are values that are closer and closer to 3, so maybe like negative 3.5, and then negative 3.1, and then negative 3.0001, as I get closer and closer, I can see that my y value is getting really close to 1. And if I approached from the right, so maybe I started at like negative 2.5, and then negative 2.1, and then negative 2.0001. As I get closer and closer, I see my y value is once again approaching approaching 1. So as I approach from the left and from the right, I'm ending up at the same value. Now in this case, there was no hole or gap to worry about, so I could kind of just evaluate and get straight to my answer. But we could use our approach method, which we'll need to do later, to find our value here, which we found to be 1. All right, let's take a look at some more examples. Consider the graph of f of x equals x minus, or square root of x minus 3. And once again, I like to keep this in mind as I work with square roots. This is the same as x minus 3 to the power of half. Well, what do we know about square roots? I can only find the square root of a number with a value of 0 or greater. So I know there are restrictions. I know that x minus 3 must be greater than or equal to 0. So that means that x must be greater than or equal to 3. For anything beyond that, it is going to be undefined. So let's take a look at what's happening when x is equal to 4. We'll zoom in. X is equal to 4, so we're just finding the value on our graph. So visually we can see that it's going to be a value of 1. And we can confirm that mathematically. So f of x equals root x minus 3. F of 4 is equal to root 4 minus 3, or root 1 is 1. So that was easy enough, and we can see that if we approach from the left or the right, we're approaching that same y value. So that looks fine. We're going to use this to look at a different example, though. So I'm going to move this over. And I want us to consider, what is the limit as we approach 3? So the limit as x approaches 3. And now remember, we said that we're approaching, when I see this limit notation, it means we're approaching it from the left and the right and finding the value that they kind of agree on. And so we're going to have x minus 3 and we are going to approach from both sides. So let's approach from the right and see what that looks like. And let me just move this over for a moment, just so I have a little more room to write. And let's make sure this all fits on the screen. I don't want anything being chopped up and getting missed. All right, quick resize. Hopefully, we're still losing something. All right, hopefully you can see everything now. Let's consider two different situations here. So we have our limit as x approaches 3, and we're going to start by approaching from the right and see what happens, and approaching from the left and see what happens. So the limit as x approaches 3, and we use a little plus sign to indicate approaching from the right. And let's finish our question here of x minus 3 is equal to, so let's zoom in. We're going to approach 3 from the right. So x is getting smaller and smaller and closer to 3. And my y value is approaching 0. So that's not too bad. Let's fill that in. So the limit of root x minus 3 as x approaches 3 from the right is 0. Let's see what happens when we approach from the left. The limit as x approaches 3 from the left of root x minus 3 equals, and so we're going to start on our line to the left of our value. So let's find our line, and there's nothing. If I'm following decreasing x values, I get to 3. What's less than 3? Nothing. The line isn't defined here. And it's not even like it jumps. It's not like it continues over here like a piecewise function or anything. There's nothing else. In fact, we already said earlier that x must always be greater than or equal to 3. So if I'm approaching 3 from the left, I have values that are less than 3. Those aren't defined. They're not possible. There is no part of the graph to look at there. So there is no limit. It's not defined. It does not exist. So let's say that. Oops. How come the limit doesn't exist here? Does not exist. Why not? Actually, sorry, I'm going to take a step back here. So it doesn't exist, that's fine. But that also means, so these two pieces kind of come together to give us our limit up here where we approach from both sides, and this limit does not exist. Why not? I thought we were able to find a value for here. Can't we just like ignore this part? No. In order for a limit to be defined, it has to exist as we approach from the left and from the right. So why not? Because can't approach x equals 3 from both sides. And just in case I misspoke a minute ago, I want to be clear. The limits don't have to be the same, but they do have to both exist. And they don't both exist here. All right, let's move on to another question. Once again, we are going to be dealing with a rational function here. So given the following graph of f of x equals x minus 1 over x minus 2, evaluate the limit given below. Quick reminder, we've already seen earlier, or we already know that we can't divide by 0. So x minus 2 cannot equal 0. So x cannot equal 2. So we need to be concerned something's going to happen when x cannot equal 2. And we see that here in our graph that my line is going along happily until I get to 2, and then something happens. It doesn't actually equal 2. And then same thing here. It approaches 2, but it doesn't actually equal 2. So there's going to be some point. There's going to be some value of x that is forbidden here. And that's what we've already found here. So x equals 2 is forbidden. And this means that we're going to have an asymptote here. I believe you are familiar with that language. If not, that's something we'll talk about more later. But it is a line that my function can approach but not intersect. And there's a more technical definition that does allow for one intersection, but we're not going to worry about that here. So basically our line can have we can have any input value, we can have any x value except for x equals 2. And so the line x equals 2 defines our vertical asymptote here. So that part is not defined. And so what is our limit as x approaches 2? So we're going to approach sorry, once again, I can't go back and change this. So in order for the limit to exist, it has to be the same value from either side. And we're going to see here why that matters, because as we're going to approach x equals 2 from the left, what happens to our output? So as we approach from the left, our value suddenly plunges, and we get a very large negative value. And so we're going to represent that as y going to negative infinity. And as we approach from the right, sorry, I reversed that. Let's fix that real quick. As we approach from the left, no, it's fine. That's fine. So we're approaching from the left. We went to negative infinity, so coming from the left, which means moving to the right, went down to negative infinity. Now we're approaching from the right, so we are moving left. Our value is going to shoot up. We're going to have very large value. So as we come from the right, y approaches positive infinity. And technically, we shouldn't think of these as values. These are just a representation. So is infinity a value? Not really. Once again, it's kind of a matter of mathematical definition. So if you want to think of it as just a really huge number, that's mostly fine for this level of math. But later on, you'll see that it's more just a representation, that it's like not defined, that it just kind of shoots up to immeasurably large values. In our final example here, we're going to be looking at a piecewise function. So this is a function that has multiple pieces. And when we see something like this, a filled in circle, that means that the value does exist there. So if this is like 3 on our x-axis, it does exist there. But if we see an open circle, that means it does not exist there. So it's like it comes right up to 3, and then it stops without touching it. Whatever way you want to think about it. So let's take a look at our piecewise function here, and let's find our limits. So examine the following graph of f of x and evaluate the limits given below. If the limit does not exist, enter DNE without quotation marks, but we're just writing anyway, so we don't need to worry about quotation marks. All right, let's take a look. First of all, we are approaching 0. So let's approach 0 from the left. So x equals 0 from the left, and from the right. Looks pretty continuous to me. I don't see any gaps or anything, and it's approaching, or it's just going to be that value there at y equals 1. So as x approaches 0, y is going to be equal to 1. Next up, limit of f of x as x approaches 3 from the left. So let's highlight that to be clear. From the left. So let's approach 3 from the left. Let's take a look at our graph. X is equal to 3. We are approaching from the left. And so that value exists. So we can see that when x is 3 from the left, my y value is 10. So we're just going to write in the 10. Erase our lines to keep things tidy. And let's take a look at our next question here, where we're going to approach 3 from the right. Let's approach 3 from the right. So I'm on my line. I'm getting closer and closer to 3. And when I get there, it doesn't exist. Like the graph stops, but it does approach a value. And what is that value? Well, we can see if we zoom in, if we get really close to 3, but not actually 3, so we're right here instead of here. What value are we getting really close to? Well, it looks to me like we're getting really close to 1. So what is the limit as we approach from the right? it's going to be 1. And notice these don't match, but that's okay, as long as they both exist. Or we're just finding them from the left and right anyway, so it's fine that they're different values. All right, so what is our limit as we approach 3? Well, remember that's from the left and the right, and this is where it's a problem. These values are not the same, so this limit does not exist. It exists from the left, it exists from the right, but just x approaches 3 from the left and the right, those values are not the same, and so they don't exist. Because why? Because 10 does not equal 1. All right, now let's try approaching 5. And it doesn't say from the left or from the right, it's from both sides, so let's actually indicate those really quick. So these limits here are the ones where we're approaching from both sides. From both, oops. Approaching from both sides. All right, we got a couple more to go through here. So we're going to approach 5. X equals 5 is right here. And it looks like the graph is going to get close to it but not reach it. It's going to be an asymptote. So as we approach from the right side, it's going to negative infinity. But as we approach from the right side, as we approach from the left side, it's approaching positive infinity. Positive and negative infinity are not equal, so they don't match. So we're going to say this limit does not exist. All right, well, let's take a look at our next one. We are going to approach 7 from the right. So let's take a look at x equals 7 on our graph. Let's approach from the right. And that value is going to be pretty close to, possibly exactly, -2. So let's fill that in, -2. Let's approach from the left. So coming in from the left. Once again, I'm getting really, really close to my x is approaching -7. My y value is approaching -2. So let's pop that in there. And we are approaching the same value from the left and the right. So when we approach from both directions here, where there's no direction indicated, that limit is also going to be -2. And now that we've worked through these example questions, I would like to kind of summarize a few things about the existence of limits. So I'm going to kind of read a couple things from the textbook here and then summarize them for you in this slide. So we say that the number L is the limit of a function y equals f of x as x approaches the value a, written as, so the limit as x approaches a of f of x equals L if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x also equals L. I don't need a double equals sign like that. But basically, has to approach it from the left and the right. Or I'm going to rephrase that in a slightly different way. Same idea. I'm going to say if the limit as x approaches a from the left of f of x equals some value L, and the limit as x approaches a from the right of f of x is also equal to L, then L is the limit as x approaches a, that is the limit as x approaches a of f of x is equal to L. So in other words, the limit like the general limit where it's not left or right, it's both, equals the value only if approaching from the left gives that value and approaching from the right gives that value. And we've kind of seen that already. I just want to write it out and state it directly. A couple other things to notice, that we've said this already too, that the limit as x approaches a of f of x can be equal to f of a. And we've seen that already, even just on this page, where I have points that exist on the line. So what is the value as x approaches 0? So the limit, so like this part here, limit as x approaches 0 of 1 is just equal to f of 0 equals 1. We can just evaluate directly because it's just a continuous line. There's no special features. There's nothing interesting or unusual happening there. So I can just evaluate. We've done that already. Finally, that the limit as x approaches a of f of x may exist even if f of a is not defined. And that's what we saw here with our asymptote, with our value of 5. So x equals 5. That value is not defined. It's not permitted. It doesn't exist on our line, but I can still have limits as we approach that value. So as I approach from, I can have a one-sided value. As I approach from the left, I can have a value of positive infinity. As I approach from the right, it can have a value of negative infinity. Or I could have a hole like I've seen before. So I could have had another graph like this. Where there's some gap. So my line is defined everywhere else. And so the limit, this is my a value. The limit as we approach the a value still exists. So let's just call this my b value. Because as I approach from the left and the right, I'm getting that same value, even though f of a does not exist. So that value, that point in our graph does not exist, but I can still find the limit as I approach it from the left and the right. So we've seen this all in our examples already. I just like how the textbook summarizes this, and I wanted to state that for you clearly so you could also take a look and understand the overall concepts that we've just applied in these example problems.